We now move on to the sixth stage, which involves estimating the parameters of the copulas. For this, we use the data U object created in the previous step, which contains data transformed into the interval from 0 to 1, inclusive. In this stage, we estimate 4 different copulas: Gaussian, t-student, Clayton, and Gumbel. Each of these copulas has specific properties describing the dependence between variables, allowing us to compare their fit to the data. We first estimate the Gaussian copula. For this, we use the normal copula function from the copula package to define the copula type and the fit copula function from the same package to estimate the parameters based on the input data. In this case, we model a two-dimensional copula. The estimated row parameter indicates a high level of correlation between the variables. Next, we estimate the t-student copula, which differs from the Gaussian copula, in that it includes an additional parameter specifying the degrees of freedom. To estimate this copula, we use the t-copula function from the copula package along with fit copula. As a result, we obtain 2 parameters, one corresponding to the correlation coefficient row, and another df specifying the degrees of freedom, which influence the intensity of the symmetric dependence in the tails of the distribution. We then proceed to estimate the Clayton copula. In this case, we use the Clayton copula function from the copula package along with fit copula. The Clayton copula models particularly strong dependencies in the lower tails of the distribution, meaning that the variables are more correlated in the regions of low values. The parameter of this copula, denoted as alpha, referred to as theta in the course, lies within the left open interval from 0 to infinity and determines the strength of lower tail dependence. The higher its value, the stronger the correlation in the lower tails. As theta increases, the correlation growth slows down because the relationship between correlation and the parameter is an increasing and concave function. The obtained parameter value is relatively high, suggesting that the dependence in the lower tails is very strong, which was previously evident in the scatter plots. The final estimated copula is the Gumbel copula, which is designed to model dependencies in the upper tails of the distribution. Here we use the Gumbel copula function from the copula package along with fit copula. The Gumbel copula has a theta parameter, denoted as alpha in the output, that determines the strength of upper tail dependence. The higher its value, the stronger the correlation in the upper tails. This parameter falls within the left closed interval from 1 to infinity, where values close to 1 indicate very low correlation. As theta increases, the correlation grows, but at a decreasing rate. The function describing the relationship between correlation and the parameter is increasing and concave. For large values of theta, further increases in the parameter result in only negligible growth in correlation.